So between episodes we unlocked general rocketry from all the new science we got. Today we are going to aim for orbit, and we're going to show you how to calculate if you're going there or not.
We are going to go for orbit. We want to try to always do two contracts in a go, because that increases our return on investment, like we're paying for the vessel, so might as well do as much with it as possible. However, let's see what we can actually do here. The only thing I can really think of that sort of makes sense, but really doesn't make sense, but gives a good payout and some science and stuff, is to test the TD12 decoupler splashdown at Kerbin. And you'll be thinking, well, haven't we decoupled all our decouplers once we splash down? Well, yeah, except if we bring one extra. So let's bring one extra and call that good. So, because the other ones are like splash down with the swivel engine, we won't do that. We won't haul the hammer into flight and all that. We'll just do that. Now, to get to orbit, we need to consider the delta V of our rocket, because we need to go sideways at 2300 meters per second. Factor in some gravity losses with that, and you find that you probably want something like 3500 meters per second, or even more when dealing with smaller rockets like this. Well, we will use a bigger rocket, don't you worry. Because okay, I'm not actually sure how I will approach this. Yeah, because we will remove that stack. That's how I will approach this. What issues we have is what is known as gravity losses and drag losses. And drag losses will factor in way more on smaller parts, which are 1.25 meter parts and below. And to minimize those, you use either bigger rockets or bigger rockets. That's like the way to get around that. But we don't have that option right now. So your basic rocket is either a solid booster or fuel and a engine to consume that fuel. Actually, fuel and oxidizer, so reaction mass as it's formerly known, and an engine which then converts that reaction mass into impulse and gets your rocket moving in the other direction. How much impulse will you get from a rocket? Now that's the question we need to answer. That question is answered by the rocket equation, and let's hope I remember to edit this, because now I want the rocket equation on screen, like show it right here, and I'll probably freeze frame. So I thought we would familiarize ourselves with the rocket equation, how it looks, how it works. We want to solve for the delta V of our stage of our rocket. We know the specific impulse of the engines of our rocket. That's this thing here. We also know that the gravitational constant is 9.81. We have used that to calculate thrust to weight ratios. We'll be using it again here. Shows up all the time. What this is, this part of the expression, that's your exhaust velocity. What this is the integral of your mass expulsion. What do I mean by that? Well, we have our mass ratio inside these parentheses, right? We have our initial mass, this is that right there, divided by our final mass down here, and then we take the logarithm of that. Why do we take the logarithm of that? Well, ideally you would want to push all your reaction mass out your back at once, right? So ideally you would say, well, I have an exhaust velocity of say like say our exhaust velocity is like 300 meters per second, and our reaction mass is one big rock, and we are just throwing it out the back of our rocket. So our rocket is here. We have a rocket nozzle which somehow fits a rocket, don't ask me how. And we are going the other way because Newton said so. We have an action and a reaction. So we're throwing this out, say at 300 meters per second. How fast is our rocket going to travel, assuming this weighs as much as the rocket?
it's going to travel at 300 meters per second in the other direction, right? However, imagine we didn't have one rock, but two rocks half the size of the initial one. We would be throwing them out one at a time. Throwing out the first one, well, we're still throwing it out at 300 meters per second. But now we have to push the mass of the rocket plus the remaining fuel, plus the remaining bit of the rock. And the total mass of that is going to be not the same as the reaction mass, but 3 times. Remember, this weighed as much as the initial rock, and then we also have half again as much. So that's 3 times as much weight we're pushing compared to our reaction mass. So our impulse here is 300 meters per second times that mass, and then the impulse in the other direction has to equal that, but we have 3 times the mass, so the resulting acceleration is only 100 meters per second now. We still have the rest of the fuel, so we push that out at the same velocity, but now, instead of having a rock that weighs well, as much or a third as the rocket, where we have a mass that is half that of the rocket. So our total impulse pushing that 300 meters per second in one direction is going to be half of 300 meters, or 150 meters per second. And then you sort of add up those impulses, and you end up with a net acceleration of 250 meters per second. So slightly less than pushing it all out at once. And that's because, well, we don't just have to accelerate our rocket, we have to also accelerate all the fuel that we're bringing along with us. You can imagine splitting this up into smaller and smaller and smaller parts, and then you would sit up and add all the reaction masses into one single long equation. But doing some calculus, as Tsiolkovsky did, and this is Tsiolkovsky's rocket equation, he figured out that, well, you can just take the natural log. It's kind of simple math, really, but it didn't really have an application before the 1800s. So, and that's when he sort of coined this thing. And from there on out, it has been very useful, because people have been using rockets a lot since then, apparently. Now, the tyranny of the rocket equation is, of course, that as you bring along more and more mass, you're not going to get, like, if you bring twice the amount of fuel, you're not going to get twice the total impulse. Initially, it's going to be very close to that. You can think of this as our thrust-to-weight ratios going up. We start at 1. You're never going to have thrust-to-weight. Dry mass ratios. You're never going to have a dry mass ratio smaller than 1. So you start at 1 initially, and then as you fuel up your rocket with more and more fuel, you get a better and better, well, you get a larger amount of delta V. This y value, you would multiply that by your exhaust velocity to arrive at your delta V. So here, at something like 2.8, 3, perhaps, I forget what E is, you would get as much, if you brought along 1.83 times as much fuel as dry mass, you would get your exhaust velocity in delta V. So for most engines in KSP, that would be between like 2.9 and 3.4 kilometers per second of total delta V. What you find is that going beyond a mass ratio of about 4.5 is usually a total waste. Simply because, well, not only are you going to accelerate slower, that's not even factored in here. Like your thrust to weight is going to be worse and worse the more you weigh initially, of course. Your dry mass is also not going to increase, stay the same as you add more and more fuel. You have to bring along more and more fuel tanks. And also you can see that as you increase your mass ratio here further and further, well, back over here when you have a mass ratio of like 20, going to 21 is obviously not giving you way more total delta V compared to going from, say, 1 to 2 over here. That gave you a lot of extra delta V. Like, the difference is huge. So this is the tyranny of the rocket equation. You want to keep your stages large enough that you get the most use of your engine, but at some point there's really no point in bringing along the stage further, so you have to sort of cut it off. You have to stage it. You have to drop off all that dead mass. And yeah, that's why you sometimes see people trying to add more and more fuel tanks, and they get no more delta V. Why is that? Well, it's the tyranny of the rocket equation.
So with that in mind, since we had to do all that, let's cut the episode short. Let's do this quickly. First of all, we're going to save this as orbit, because we want to keep the skyscraper pod for later. So we can later go to the skyscraper and pull it with all the science experiments. The only 2 science experiments we really want to run up there are probably going to be these 2, because if I recall correctly, we got the Mr. Goof from space. So we bring those, we bring the pod, and that reduces our dry mass of the rocket. Imagine that. And since I explained that so thoroughly, you know why dry mass is important to reduce, to get the most amount of delta V. Now, for the practical example here, we are going to do this in one stage, because then we only have to calculate the delta V once. You have to do it for every stage, and usually you end up with 2 or 3 to go into Kerbin orbit, because that gets you the most use out of your engines. But we can do a single stage to orbit in KSP fairly easily, using almost any design. That's not entirely true. What I like to use for these tall stacks is auto-strutting all the engines to the root part. That is unlocked only once you get to the tech node, which includes struts. So we can't do this early on. We'll have to be a bit careful about that. And since this will probably tend to wobble a bit, and since we are going to steer it manually because we don't have any autopilot mods, we are going to add basic fins to the whole arrangements. 3 of them to reduce the amount of stability we get, so we still retain some control, and we're going to put them just below the center mass, which of course looks ridiculous, but that's the best place for them. As these fuel tanks drain out, they will drain evenly nowadays. It used to be so that this top tank would drain first, and then that, and then that, and your center mass would shift backwards, which would mean you started out stable and then you went unstable. As it is now, our center mass will move backwards slightly, actually, because this engine weighs more than the pod up top. So with that in mind, since it will shift slightly backwards, we're going to move those slightly backwards as well, just for margins. Once that becomes an issue, we'll be way out of the atmosphere, but better safe than sorry. How many fuel tanks have I added now? What I estimate to be a good number. Our thrust is 167, our weight is roughly 100 kilonewtons, and that comes out to a thrust-to-weight ratio of about 1.67. Very simple math there. And I think that's still a bit too much, so let's add another 2 of those and move these up a bit. The more fuel you have, the higher delta V you will have. Remember the rocket equation. So how much fuel is this? Well, we can sort of figure that out, can't we? One way to do it is to drain these tanks one by one, go through the entire stack, check your mass then, and then fill them again and see what you started out with. And then you will know your wet mass and your dry mass. Now, because we only used one tank type, like we did here, and we know this tank type contains 90 units of liquid fuel and 110 units of oxidizer, or if you check the mass here, 450 plus 550 kilograms of reaction mass. That means for each tank we have 1 ton of reaction mass. 550 plus 450 is 1,000, or 1 ton. 1, 2, 3, 4, 5, 6, 7, 8, 9 tanks means 9 tons of reaction mass. Yay! Okay, so then we, well, I switch recording modes. You don't have to worry about that. And we do our rocket equation. Now, that was our initial mass. Remember, we wanted the mass ratio, so our initial mass is 12.6 tons. We want to divide that by our final mass to get our mass ratio. Our final mass is 12.6 minus 9 tons. So that comes out to 3.6, right? I'm not daft, am I? No, it's 3.6. That means our mass ratio is 3.5 tons. What we do then is take the natural logarithm. For this to work in Windows, you switch to scientific, like we can switch to standard, it looks like that. Scientific gets you all the things you need. And also removes our number. We had 3.5 as our mass ratio. Our natural log of the mass ratio is that. We multiply that by our exhaust velocity. And the readouts in Kerbal Engineer are all in vacuum, so it takes 320 in vacuum, and that's sort of the standard everyone uses. Vacuum delta V is what you are concerned with, and that's what people sort of reference when you talk about how much delta V you need to get into orbit of Kerbin. So we multiply that by our exhaust velocity, which is 320 seconds times the gravitational constant. And I'm sure someone can explain why that is. It's because it converts easily from metric to imperial. Anyways, that means this rocket has 3,932.7 roughly delta V, which according to most guides is okay. I mean, as long as those guides are written like after 2015 sometime. So this will get to orbit and back using one stage, and that's excellent. Anyways, this episode is already long enough, so we'll see the fruits of our labor in the next episode when we'll go to orbit and hopefully back again. So see you later, I'm Gaspatian.